Hello everyone, I'm Francesco Utele and I'm a member of the Engicam support team. Today I'm gonna talk about a powerful tool that Engicam provides to its customers, that is the Engicam BSP. This is basically a platform that lets the customer create in a quick and easy way the software for his embedded system. Here's the outline of this webinar. We will start making a presentation of an hardware example of Engicam system on module and board. Then we will talk about the main topic of the webinar, that is the Engicam BSP. And of course we will need also to make some Yocto Basics in order to let the audience understand better how to use the BSP and get the real take-home message of this webinar. And in the end we will also make an example combining the hardware of the first part with the software generated with the Engicam BSP to run a Yocto image on the embedded system. Let's start from the hardware. So the Engicam system on module that will be used for this example is the iCore MX8 Mini that is equipped with an NXP processor. Its cores are a quad-arm Cortex A53-3 and also for real-time graphical application a Cortex M4. Support any kind of peripheral and it can run both with Linux and Android. What I would like to stress about Engicam module is the fact that they are actually part of the EDIM standard. Many of you maybe know the SODIM standard, that is a mechanical standard. That means that you can plug and unplug your system on module from a board. But Engicam create this internal standard for this product that make a further step of compatibility, because all the modules that follow the EDIM has also specific configuration in the system on module pins output. This means that if you have two different modules that are both EDIM modules, you can plug them in the same board without any change from a software point of view. And there are several advantages for this approach, because as I just said, there is compatibility with the modules, but there is also scalability. So if you are creating a system for a specific application with an EDIM system on module and you realize that you have not enough computational power, you can just unplug the module they are using, plug another module with a different processor and a higher computational power, and then keep on developing your system. So there is compatibility and also complete scalability. Then other important feature of the Engicam product with the NXP modules are the longevity program that grant long-term production availability, and the robustness of the Engicam system module as we perform tests also under thermal and mechanical stress. Now let's keep on describing the hardware that we are going to use in this presentation. I told you about the system on module. Now I will introduce you the board that we will use with the MX8 Mini, that is the EDIM Starter Kit 2.0. You can of course check on the website also the other board and all the peripherals available. And this is a picture of the starter kit. So basically it's EDIM compatible, of course, and once you plug any EDIM module here you have actually support for all this peripheral, but you're gonna see it later in the video. Let's move now to the main topic of this webinar, that is the Engicam BSP. The Engicam BSP is basically a virtual machine that Engicam provides to its customer, already configured and ready to use. That means it's ready to let the customer develop its software for his embedded system. You will find inside the virtual machine the Yocto sources already installed. For whom of you do not know what Yocto is, we are gonna go deep into this topic later, but right now just think about it as a set of tools that allow you to create your customized Linux distribution for embedded system. Of course, you will find also the system on module toolchain already installed that you can use to cross-compile your applications for the target host. And you will find also a Qt Creator already set up with the kit, with a specific kit for your Engicam machine. The Engicam BSP is a virtual machine image for VMware, so if you are gonna use VMware, then it will be really quick to start to work with it, because you just need to open VMware and start the image. Otherwise, if you prefer to work with the VirtualBox, no problem at all. There's just one further configuration step to do, that is to mount the image as an hard drive on the virtual machine. So still really quick and easy to use. As already said, one of the features of the virtual machine of the BSP are the Yocto sources. So I'm now going to explain a little bit what Yocto is and how the user can exploit it to develop his own Linux distribution. So basically, the Yocto project is a combination of tools, and the aim of the project is to basically improve the software development process for embedded Linux distribution. The keyboard here is customization. So many of you that have experience with Linux knows what a package management system is. So you install your Linux distribution, the one that you choose, then you start to add packages with the package management, and in the end you get your customized version, of course, with customized packages. With Yocto, the customization process is completely different, because you start to customize the sources, adding packages, and then you perform the build of the operating system. So the difference here is that you can customize your Linux distribution at the core. And it has many advantages, because actually it guarantees to create, every time you make a build, you perform a build of the operating system, exactly the same version. It means that you do not have to install again a generic Linux distribution and start to add packages. You can just compile your customized Linux distribution and plug it directly in your hardware and start to work with it. And another important feature is the fact that you have a really high degree of customization. You can really create a very light operating system suitable to run on really low computational power embedded hardware or embedded system, but at the same time you can also create very complex featured images for more complex machines. Here you have a picture of the flow of the build process with Yocto. You start from the left, where you have the configuration of the build. So you start from a low-level configuration, that is the machine configuration, and this is something specific for the hardware. Then you have a higher level configuration, that is the user configuration level, and a whole set of .bb and patches that are called metadata. We will see later what actually they are. .bb, it means basically that this file is a BitBake recipe. I'm gonna talk about it. Then when all the configuration files are ready, the build process starts. There is download of the sources from the online mirrors, or they can actually be on the storage drive where the build is run on the host. There is this configuration step, and then the packages suitable to be installed on the target machine are created. And in the end, all the packages are merged to generate a final image and the final toolchain. So I told you that there's a build process in Yocto. So you start from sources file and you perform a build. The core of this sources file, that is the reference build system, is Poke, a set of tools and packages that are gathered in layers. A good starting point to create a first fully featured build. Then the heart of the build process, BitBake. So I just said that Yocto is a collection of toolkits. One of these toolkits is Poke, that is this set of sources. But then you need a software that can glue together and handle all these different packages sources to create a final image. And this tool is actually BitBake. That is a make-like. So from whom of you already know how to use Make, it will be probably quite easy to understand how BitBake works. And it performs cross-compilation of the packages. What is cross-compilation? Basically, we are creating an operative system for embedded Linux, for embedded architectures. It means that we are probably performing the build and the customization on a machine that is different from the machine on which this operative system will run. So cross-compilation is exactly this, is compiling code for a computer system on a different system, called the host. Here's some historical concept. BitBake is inspired by Portage, which is the package management system used by Gentoo Linux distribution, and it is co-maintained by both the Yocto project and the Open Embedded project. Open Embedded is another project that provides a toolkit for embedded Linux operative system cross-compilation. You can find more information about it online as well. Now let's talk about how BitBake works. We said that inside the Engicam BSP you will find this directory, that is the Yocto source directory. Inside this directory you will have several meta layers, and inside these meta layers you will have the BitBake recipes for different Linux packages. In these recipes there are the instructions that BitBake follow to compile that specific package. So there will be a source mirror, and there are several protocols available to download the source code and of course it can be both online and on the local system. There will be the dependencies, so in the recipes there will be the name of the other packages that have to be compiled to include the package in the final build, and other compilation or installation options. Another thing that you need to know is that during the cross-compilation, BitBake generate as a first step the toolchain. A toolchain is a set of compilers for the target. So this means that before the compilation, BitBake generate a toolkit that we use to compile the packages on the host machine that will be part of the final image. To summarize this concept, we can say that during the build process, recipes are used to track dependencies, performing native or cross-compilation of the package, and package the output of this cross-compilation to make it suitable for installation on the local or on a target device. And it is also possible to create complete images consisting of root file system and kernel. Here you have an example of BitBake recipe. This specific recipe installs the tools for eMMC programming. Here you have all the licenses specification for this package. Then you have the source URI, in this case is a script on the local drive. Then you have the other package from which this tool depends on, and then you have the do install function that specify BitBake how to move this source file or the output of the compiled package in the root file system that it will create at the end of the compilation. So here's again a sequence of steps that BitBake do. So at the beginning there is the do fetch that I told you about. So it basically gets all the source file, it unpack the source file with the do unpack, it apply eventually patches with the do patch. Then there is the do configure. You know, we said that BitBake is a make-like tool, so if there is a configure file, it will be launched in the do configure. Then there is the do compile, the compilation step, the build of the package. And then on this other line, there are all the tasks that BitBake perform to move the package that has just been compiled to the final image. So there is the do install, like the one in the example of the previous slide, that tells where in the root file system put the file related to the package. Then there is the do populate system root that actually take all the root file system of that takes all the root file system on the temporary working directory of Yocto in what will be the final image. Then it performs other 3 steps of do package where it actually creates packages for all the tools included in the image in order to make possible also to install them later without repeat the fetching and the compilation steps. This is the layer of BitBake. I know it might seem that we are telling you lots of concepts, but everything will be more clear immediately when we will give you an example of BitBake compilation. And inside the sources, inside the Yocto sources, you will find meta layers. There are default meta layers like Meta Yocto or Meta, which are those that you will have immediately if you download from either the Open Embedded or the Yocto project website, the build system. And then there are several types of additional meta layers that you can add to your sources to perform other customization. For example, we have here either the Metal Intel or the Metal Fiske, which are meta layer with packages that are hardware related. Then you have this other type of meta layer that contains packages for kernel module compilations. Then you have a software layer where there are just recipes to compile software that you need in your image. We have as an example here Meta Baryon, or you can think about Python. There is a meta layer called MetaPython that actually has all the recipes to install Python and its module on your image. And then in the end you have custom layers that are actually the meta layer that you can build for your specific model, adding recipes of any kind you want for that specific project. Here an example of the structure of the Engicam meta layer. What you need to remember is that the Engicam meta layer has a configuration folder with all the configuration files for the different Engicam machines. Then you have a different group of recipes that can be either BSP specific or they can contain software for the connectivity. So in this case, the firmware for the Wi-Fi antenna, and then also other recipes for hardware tests, or in the end, the most important one, and you will see as you will see later, the operative system image that gather all these other recipes to create the final operative system. Another thing is important to know is that if you are developing a Linux distribution for an embedded system, you will also create in the build process a device tree. That is a tree of nodes where the pin out of the processor are configured to work with specific peripheral and active components. Here we have an example of device tree nodes. So we have a pin control. The pin control is another node when you will specify which pinout of the processor will be used to work with that peripherals, and of course there will be defined inside the node also the interrupts. So everything I talked about is inside the Engicam BSP sources. This is open and available on our GitHub repository, that is github.com Engicam stable. If you do not want to use the BSP inside of a virtual machine, no problem. You can just download the Yocto sources of the distribution you want, and then afterward from our repository add the Meta Engicam layer. And to conclude, remember that if you need any help for anything, just contact our support team at the address support.engicam.com. So the description of the Engicam BSP is now over. Let's just jump into it and start to play with a virtual machine. So we just opened with the VMware the virtual machine image containing the Engicam BSP. This is how it looks like. This is Ubuntu desktop. Let's start to explore the Yocto sources folder. As we said before, this is an example where we are going to compile an image for iCore MX8M Mini. And the Yocto distribution, the Yocto version on this virtual machine for this purpose is Sumo. So we are now moving in the Yocto root directory. We can see that there is another folder that is Sumo, the name of the distribution. And finally, we are in the directory where the environment variable, setting script, and the Yocto sources folder are placed. Moving inside the sources folder, we can see that there are other subdirectories. All these directories are the meta layers that we talked about. So the first thing you need to do is to update your Meta Engicam layer. This one is called Meta Engicam MX8 because it contains the source code for the MX8 processor family, but there are Meta Engicam layers for any kind of machine produced by Engicam. So let's move inside the meta layer. As we said before, it is a Git repository, so it can be updated with the command git pull. In this case, it's already up to date because this is a new virtual machine, but it's strongly recommended to perform this step every time you open the first time the virtual machine. In the previous part of the webinar, we saw lots of concepts about Yocto. What is important about the Engicam BSP is that everything is already set up to let you compile your image without performing any configuration. We have two different recipes for this purpose. The first one is the Engicam test hardware. That is a basic image that allows you to perform hardware tests and so start to test the peripherals and learn how to interact with them with the software on the SOM. And the other image is the Engicam Demo Qt. That is a more complex image as it also contains all the Qt library, and this is extremely helpful if you want to start immediately to create graphical application that should run on your system or module coupled with a display or a touch screen in general. And for this purpose, the virtual machine comes with a Qt creator already configured. Let's open it. Already configured with the kit, with the specific kit to start to deploy the Qt application straight on the target. You can see it here. Let's now see how to build the image. So, first thing you need to do is to set up the environment, specifying the machine you're going to compile the image for. So, all the available machine can be found in sources, Meta Engicam conf machine. And you can see that here there is the configuration file for the iCore MX8 and Mini. Then launch the following commands. We are in the Yocto root directory. We are specifying the machine we are compiling the image for, so the iCore MX8 and Mini corresponding to this configuration file. Then we launch also the script that set the environment variables for Yocto compilation, and then we define the building directory name. So there is now the licensing to accept. Then you need to add to BitBake list of layers the Meta Engicam MX8. And finally, launch the compilation of the Engicam Demo Qt image, the one with the Qt libraries. And that's it. Now BitBake is compiling the full image, nothing else is required. As I already said, easy and quick to do. And after the compilation will be over, I will show you how to flash the output image on an SD card to start for the first time the iCore MX8 and Mini with the Engicam starter kit board. Let's now jump straight at the end of the compilation. The build procedure can take also several hours. It depends from the kind of image you are building, so the number of packages included in it, but also it depends from the computational power of the host machine. Despite it might seem lots of time, you need to know that if you perform again the compilation, it will take way less. This is because BitBake will not perform again the fetch nor the download of the source code from the mirrors, because everything will be stored in the download folder. So if you just need to add a single package and compile again the image, you can add the package to the recipe, in this case to Engicam BSP, and start again the compilation. And it will take only the time required to compile that package and to populate the system root image, the final step of the BitBake compilation. So, as I told you before, let's now flash our image on an SD card. The SD card is already inserted in our SD card reader, so we need to move to the folder containing the image. So let's move to the temporary folder, that is the one that contains all the files created during the build. You can see that there are inside the TMP directory, there are several other folders. The one that we are interested in is deploy, so we'll move to TMP deploy. Here you have again other 4 subdirectories. This one, SDK, is the one where the toolchain is deployed, so if you need to install the toolchain, you need to move to this subdirectory and launch the installation script. We now enter the images folder containing iCore MX8 subdirectories. Basically, if we will perform a build for different machines, here in this folder we have found a deploy directory for each one of these machines. We just compiled the Engicam BSP for an iCore MX8 machine, so this is the only folder actually in this subdirectory, and these are all the files related to the compilation. So we have the bootloader image, we have the image.bin, in this case this is the kernel of our compilation, and also the device tree of the kernel, the .dtb file. This one, .sd card, is a full operative system image that you are gonna flash on our SD card. We will exploit the dd command of Linux. The input file will be our .sd card, and the peripheral we are gonna flash on this image will be our SD, plus other options that you will find, of course, on the manual. We need to perform this operation as super user, so we need to insert the root password, and that's it. Now the system is flashing our .sd card file on the SD card, and we are now ready to use this SD card to perform the first startup of the iCore MX8M Mini on our eDIMM board. But before, let me show you one last thing that might be useful, that is to set up a shell to communicate and to access the module console. Of course, the tool you're gonna use depends on the operative system you will use to connect to the console, connect to the module console. It can be, if you're using Windows, you can use PuTTY, you can use TerraTerms. If you're using Ubuntu, one way is to use Minicom. So you can launch Minicom with the -S option. That means running it, opening the setup that allows you to correctly configure the communication with this shell and the module. So you should define the serial device. If you're gonna use the serial USB converter, the driver on Ubuntu will be probably give you a device like this one. You have to set the baud rate as 115 to 100, and you have to be careful to have both the hardware and the software flow controls set to no. And then to just run Minicom, select exit. Okay, so let's start our module. This is the SD card we just flashed. We plug it into the board. We now plug the system on module, the iCore MX8M Mini, on the board. We connect the serial cable to the serial USB converter. This is the cable we use to communicate with the system in Minicom. This is a jumper used to select the boot partition, the SD card in this case, and we now plug the module. This is what is happening in the meantime on the console. So immediately when we plug the module, the system starts to load the kernel, and finally it loads and mounts the root file system. We insert now the password, and that's it. We are inside the console of the system on module. So let's now see what is happening on the display of the system. The root file system has already been loaded, and there is a script that automatically, at least in this image, there is a script that automatically launches a browser with a web page with several graphical demos available. So that's it. I hope you enjoy our webinar, and don't forget that for any question about the NG Cam BSP, you can contact us at support@ngcam.com.